So say suppose we've got a circle. Hey, we've got a circle. So from our circle, let's have something like this. Then we also know that we have a center. So this is one of the special theorems that I like to teach because it has hidden theorems in it. We've got a center, then let's have an angle subtended by A, AB. Then let's have a C somewhere here. Then let's have C also subtended by AB. Okay, don't know what just happened. Okay, so let's also have C subtended by AB. I'm searching for this. Okay, so we've got our C there. So I think we already know that the theorem states that if we have x here, then we must have a 2x here. Okay, it states that angle from circumference subtended by the same arc or chord as angle from center implies that angle from center is twice angle at the circumference. Okay, so what I'm gonna do is this. We want to prove that is it really true that if we have 2x here, then we have x here. So in order to prove that, remember something. You must include the obvious. And the obvious here is that line from center to circumference is what is called the radius. So which means that these lines are equal. And let's have this as ABC. Let's have this as D. Then from here, let's also include an obvious thing. Line from center to the circumference is also a radius. And let's have this radius passing through the center by some margins. Then which means on this side we have D1 and on the other side we have D2. Here we have C1, then we have C2. Now can you see that we have isosceles triangles? That we have two sides that are equal, which means that if I have this as a radius and also this as a radius, if I have a C here, then I'm also going to have a C here because they are all opposite equal radius. Then if I have a C2 here, then even here it's going to be a C2 because we have opposite equal radius. Now here's an interesting thing. If we have a situation of a triangle and we have x1 and x2, then we have y here. Then y, which is the external angle of a triangle, will be the sum of the opposite side. Okay, so if we apply this theory, that external angle of a triangle is the sum of the opposite side, we are going to have that D2, this D2 is equals to C2 plus C2, which is 2C2. And we can have that D1 is equals to C1 plus C1, which is 2C1. Then this must give us the whole of D, which is D1 plus D2. And this is equals to 2C1, this is supposed to be 1, plus 2C2. And we can have this as 1 plus 2. But this is the whole of C. And C is actually 1 plus 2. So we have proven that D is 2C. Okay. So that is one special theorem that I will want to repeat on a Saturday. So I was just giving you a taste on what to think when you're proving this theorem. And what is key here is we can have the same setup if we have another angle from this point maybe to there and joining in like that. If this is maybe f and we draw the same thing, we will have the same result. So which means that at the end of the day, if we are applying the same thing and we get the same result, f is equals to c can be proven that angles in the same segment are equal provided they are subtended by the same chord. We are using the same theorem that angle at center is twice angle at the circumference to prove that angles in the same segment are equal. So that is very, very interesting. So guys,